Okay, this is video 3 for the torque unit notes, and this will be the final video. Okay, we have talked about equilibrium before when we talked about our notes with forces. And basically, for equilibrium, what that means is that there is no acceleration. There cannot be any acceleration. There can be movement, though. If an object's moving at a constant velocity, it can be in equilibrium. Or if an object's at rest, it can be in equilibrium. Now, when we talked about equilibrium before, we said this. We said that the sum of forces on the x-axis have to equal 0. The sum of forces on the y-axis have to equal 0. But now we can add one more thing. The sum of all torques must equal 0. Now we can have true equilibrium, where nothing is accelerating on the x-axis, nothing is accelerating on the y-axis, and nothing has an angular acceleration. All right. Now this next one, save plenty of room as you write this. In fact, you may want to pause the video here and get a separate sheet of paper and put these on a separate sheet of paper, because this does take a little bit of space to work out. It's nothing hard, but it does take a little space. This is a classic problem that every physics teacher from high school to college loves to ask. And it's very practical too. What's the minimum angle that you can put a ladder up before it slips? I'm sure some of us have done this before. You've climbed a ladder just to have it slip out from underneath of you and you get hurt. So we want to do something about that. We want to calculate what is the minimum angle before this slips. All right, now, every problem starts with a good force diagram. So we want to get all of the forces acting on this. So here's what we have. I'm going to make a couple assumptions here, and I'm going to make a few rules, I guess. I'm going to say M1 equals mass of the ladder. I'm going to say M2 equals mass of the person. L will be the length of the ladder. And US will be the coefficient of static friction just for the floor. We are going to assume that there's no friction on the wall. So no friction up here at the top where the wall is. And again, our question is, what is the minimum angle? All right, this is going to be fun. Okay, so first off, let's look at the ground. We know that we're going to have a normal force here at the ground, and we're going to have a normal force up here at the wall. Remember that normal forces are just where the surface is pushing back on the object. But because I have two of them, I need to tell them apart, so I'm going to call this one normal force 1 and this one normal force 2. This ladder wishes to slide away from the wall, so that means that there must be some friction directed towards the wall, because friction opposes sliding. What we want to study then is what that angle right there needs to be. That's what we want to find. Okay, this ladder has mass, so up here we're going to have a gravitational force, Fg1, that's for the ladder, and then we have a person on the ladder. I'm going to call that Fg2 for the person. Now, notice, this is kind of cool. Just like with a ramp, our angle theta can be found right here and right here. So that angle theta is found in those two places as well. All right, I think we have everything we need to get started. So the first thing we want to do is we want to take a look at all the forces. And let's start easy. Let's take a look at the forces along the x-axis. The forces along the x-axis, if it's in equilibrium, need to equal 0. So what we have then, just on the x-axis, is we have that Fn2 minus the static friction. And that must equal 0. Okay, so let's go ahead and plug some things in. Fn2, now friction is the coefficient of friction, mus, times the normal force, and this is normal force 1, has to equal 0. And that's as far as we can go. So this gives us our first equation. Okay, now let's take a look at the sum of forces along the y-axis. Okay, for this one, we've got that Fn1 pointing up, minus Fg1 minus Fg2 has to equal 0. Okay, so that means that Fn1 minus m1g minus m2g equals 0. Now notice what that does for us is it gives us a formula that we can plug in for Fn1. Fn1 equals m1g plus m2g. So we can plug that in. So this is like our formula 2. So what that means then is if we go back to formula 1 up here, we have Fn2 minus mu s, and then Fn1 is m1g plus m2g equals 0. So hopefully you can see that where I took this and plugged it into the normal force Fn1. All right, we've done the first two parts of equilibrium. We've said that the sum of all forces equals 0 on the x-axis and the sum of all forces on the y-axis equals 0. Now for the third part to equilibrium. The sum of all torques equals 0. That means we need to choose a pivot point. Now I'm going to choose my pivot point to be down here at the ground. Because torque is a force times a lever arm distance. That means that the Fn1 has no torque and the friction Fs has no torque. Also remember that torques that go counterclockwise are positive and torques that go clockwise are negative. Okay, something else. Only forces that are perpendicular to the lever arm. Only those forces that are perpendicular cause a torque. So this Fg2, we want to get its perpendicular component. This Fg1, we want to get its perpendicular component. All right. So notice that Fg1 and Fg2 create positive torques. So we've got Fg1, but to get its horizontal component, I have to use the cosine function. And the lever arm distance from here to here, for FG1, is half the length of the ladder. Okay, plus FG2 cosine theta. Now this lever arm distance, I haven't given that to you yet. Just for the time being, let's say that this person right here is 5/6 of the way up. I think that seems pretty reasonable. So for the lever arm distance here, let's go with 5/6. So 5L over 6. Minus. Now, the last force up here is the normal force. So check that out. Now this normal force, if we look at theta, if this is theta, then our theta will be right here. And we want to get a perpendicular component. Well, that would be the same as this right here. So notice that we can use the sine function to get that perpendicular component. So this last one will be the normal force Fn2 times sine of theta times L, because that's the entire length of the ladder. And that all has to equal 0. Okay, well, looking at that then, we can replace FGs with MGs. Also, I hope you noticed that the L's will cancel out. We could factor out an L and divide it over, so that would be 0. So here's what we're left with. We got M1G. Actually, let me rewrite that. 1/2 M1G times cosine, not sine, cosine of theta, plus 5/6 M2G cosine theta. And I'll go ahead and equals Fn2 sine theta. Well, if you think about it, I want to calculate theta, so I have everything I need except for the normal force, Fn2. I have no idea what that is until I look at my equation 1. If I look at my equation 1, I think it becomes very clear that Fn2 will be that mu times mg1 plus mg2. So let's go ahead and plug that in. Okay. Now, on the left side of the equal sign, I can factor out a cosine theta, and I can divide that over. When I do, I would have a sine divided by a cosine. Well, that gives me tangent, so that takes care of that. Also, I could factor out a g. I could take my mu, I could take all of this and divide it over. And when it's all said and done, here's what I'm left with. Actually, before I do that, notice in this equation, notice that g's will cancel out. Think about that for a second. We can factor out g's, and those would all cancel out. So this doesn't even matter what planet we're standing on. That's how cool this stuff is. So what I'm left with then is tangent of my angle equals 1/2 m1 plus 5/6 m2 divided by mu s times m1 plus m2. And from this expression, we could then use the inverse tangent to calculate what theta would need to be. And that's a lot of fun there. Make sure you go back and take a look at this math. Make sure you understand how to work through this algebra. Now, This is a little above and beyond AP Physics 1 because in AP Physics 1, you'll be given equations with 2 unknowns. This equation has 3 unknowns. So I very much doubt if the AP curriculum would give you a problem this difficult. But I want you to see it at least once because, college physics professors like to ask it. All right, so let's take a look at a problem that definitely will be on the AP exam. We have 2 rocks placed on a long wooden plank. One of the rocks is 4 times more massive than the other. Each rock is placed on the end of the plank, and we have a fulcrum that we can move. Where would we need to place it so that the system is in equilibrium? I hope that you can all see that the fulcrum would need to be placed closer to the larger mass. Hopefully that just makes sense. So, again, for equilibrium, the sum of all forces need to equal 0, and the sum of all torques need to equal 0. So let's start with our force diagram. I'm going to have a force here. I'll call it 4Fg because this force right here is just going to be Fg. The fulcrum is going to exert an upward force. Also, this 4G mass is trying to do a positive torque, while this mass is trying to do a negative torque. Okay, so the forces really are going to be pretty simple when I take a look at them. So the net force will be this force minus this 4Fg minus this Fg equals 0. There's really not a whole lot I can get out of that. So instead of focusing on the forces, let's focus on the torques. Now I need to establish a pivot point, and I'm going to establish the fulcrum to be my pivot point. That means that as force has no torque, I don't need to worry about the torque for that force. So, torque, its definition, is a force that's perpendicular to a lever arm distance. This whole plank has a length L, so let's say that this has a lever arm distance of x, and this is L minus x. So if the entire plank has a length L, hopefully that the x and the L minus x makes sense. So that means that for the positive torque, I have this 4Fg times x minus this Fg times L minus x. That needs to equal 0. All right. Well, again, I kind of hope that you can see this. The Fg's would factor out and cancel away. So I would be left with 4x minus L plus x equals 0. Or 5x equals L, or x equals 1/5 the length of L. So this fulcrum would need to be placed 1/5 the total distance of the plank away from the 4m mass. All right, well, this concludes our unit notes on torque.